Imagine a sprawling highway system, but instead of smooth, high-speed lanes, you're constantly stuck in a chaotic, totally unpredictable traffic jam. That was pretty much the state of early digital networking. To solve it, engineers realized they couldn't just build a wider road, they had to completely redesign the vehicles. So in today's explainer, we're unpacking that revolutionary redesign, Asynchronous Transfer Mode, or ATM. It's a foundational technology that absolutely changed how digital data travels across the globe. Here is our quick roadmap for this explainer. We're going to start with the variable packet problem, move on to ATM's fixed cell solution, dive deep into the adaptation and ATM layers, and finally wrap up with some real-world applications. Section 1, the variable packet problem. Okay, picture this. Have you ever been stuck on a one-lane highway behind a massive, incredibly slow-moving semi-truck? It doesn't matter if you're driving a lightning-fast sports car. Your speed is entirely dictated by that giant vehicle dragging along ahead of you. Well, this isn't just an annoying road trip scenario. It was the exact structural problem plaguing early data networks. Unpredictable, massive chunks of data were stalling out the entire system. Think about a multiplexer trying to combine different data streams. If one input line gets hit with a massive packet of data, it essentially blocks the intersection. Because that packet is so incredibly large and variable in size, the smaller, quicker packets waiting right behind it on the output line are severely delayed. The whole network gets choked by its own lack of uniformity. This variability creates highly unpredictable traffic. And to manage that kind of chaos, switches, multiplexers, and routers end up requiring really elaborate, highly complex software. They need these massive headers just to explain to the network exactly how big the incoming packet happens to be. Because of this, providing a consistent data rate, which is absolutely vital for real-time stuff like voice and video, becomes virtually impossible. Section 2, the fixed cell ATM solution. Enter asynchronous transfer load. This is a cell switching and multiplexing technology, and honestly, it's a brilliant hybrid. It takes the absolute best part of legacy circuit switching, which gives you guaranteed capacity and a constant transmission delay, and marries it with the flexibility and efficiency of packet switching. By using highly organized routing paths known as virtual circuits and virtual paths, ATM provides incredibly scalable bandwidth, stretching from just a few megabits per second all the way into the gigabits. But how exactly does it achieve this hybrid perfection? Well, it all comes down to one magic number, 53. In the world of ATM, 53 is literally everything. Instead of packets coming in all shapes and sizes, ATM forces every single piece of data into a fixed-sized container of exactly 53 octets, or bytes. Every vehicle on this network is now the exact same compact size. Let's break that number down, because it's a hyper-efficient structure. Out of those 53 bytes, exactly 5 bytes make up the header, so all your routing information, and exactly 48 bytes are reserved purely for the data payload. Because this size is fixed and never ever varies, network switches don't need complex software to calculate where a packet ends. They literally just count to 53 and move on to the next one. This skyrockets the data rates and practically eliminates transmission delays. So when we compare our earlier traffic jam to ATM multiplexing, it is night and day. Because all the cells are the exact same 53-byte size, they slot seamlessly into the output stream. There's no massive packet hogging the line anymore. It's just a smooth, orderly, sequential flow of uniform cells. But of course, real-world data isn't naturally 53 bytes long. So how do we actually get the data into that shape? Section 3. Inside the adaptation layer. To connect existing packet networks to an ATM network, we use the Application Adaptation Layer, or AAL. You can think of the AAL as the master translator. It accepts the variable, messy transmissions from upper-layer services, whether that's a constant stream of voice audio or intermittent bursts of data and video, and meticulously chops them up into our perfectly uniform fixed-size cells. Now, ATM supports different service classes to handle different traffic needs, like variable, available, and unspecified bit rates, usually called VBR, ABR, and UBR. But let's zero in on AAL1. This one is designed for constant bit rate, or CBR data, like real-time digital phone networks. It works in two distinct steps. First, the convergence sublayer, the CS, takes the incoming bit stream and divides it into 47-byte segments. Then it passes that down to the segmentation and reassembly sublayer, the SAR. The SAR adds a 1-byte header to track sequencing, and 47 plus 1 gives us exactly the 48-byte data payload we need. We can contrast that with ASCL5, often called SEAL, which is used for data rather than voice. See, data doesn't need the strict constant timing of a phone call. It usually operates over a point-to-point link. Here, the convergence sublayer accepts massive chunks of data. We're talking up to 65,535 bytes. It tacks on an 8-byte trailer and some padding, and then simply slices the whole thing into unaddressed 48-byte chunks. Because the link is point-to-point, the cells travel sequentially, meaning they don't need individual sequencing headers packed inside the payload. It's built for highly efficient bulk transfer. Section 4. The ATM layer explained. At the exact moment of encapsulation, the ATM layer accepts that 48-byte segment from the AAL sublayer we just walked through. Then, it slaps on the critical 5-byte header. This header contains the virtual path and virtual circuit identifiers, which is the exact routing and traffic management data the network needs to deliver the cell. 48 plus 5 equals our magic number, 53 bytes. The cell is now fully formed. From here, it's handed down to the physical layer, ready to be blasted across the medium like optical fiber at lightning speeds. But to really appreciate this, let's zoom back out and see how this elegant structure operates in the real world. Section 5. Real-world ATM applications. ATM was originally designed for massive wide-area networks, or WANs, but its sheer speed meant engineers naturally wanted to use it for local area networks, or LANs, too. There was just one fundamental clash. Traditional Ethernet LANs are connectionless. They just blast data packets out using physical MAC addresses, which easily supports multicast and broadcast. ATM, on the other hand, is completely connection-oriented. Before ATM can send even a single cell, it must establish a dedicated path using a virtual circuit identifier, or VCI. It is strictly point-to-point. To solve this clash of protocols, engineers created LANE, Local Area Network Emulation. Essentially, LANE acts as a brilliant disguise. It allows an ATM switch to behave exactly like a traditional connectionless LAN switch. It lets end stations use their traditional MAC addresses and allows for broadcast delivery, all while smoothly riding on top of the strict, connection-oriented ATM protocol underneath. It pulls this off using a very clever client-server approach. When a client actually needs to send data, it contacts the LANE server, or LAS. The server creates that required virtual circuit between the source and the destination. But what about broadcasting data to everyone? That is where the bus comes in, the broadcast and unknown server. The bus maintains a permanent virtual circuit connection to all stations. When a client sends a broadcast frame, it goes straight to the bus, which then copies the frame and blasts it out to everyone on the network. It's an incredibly elegant workaround that lets legacy networks tap into the blistering speed of ATM multiplexing. Which brings us to our final thought for this explainer. ATM might seem incredibly strict, forcing every single piece of the world's data into a rigid 53-byte box. But it was precisely that rigid mathematical organization that solved the variable packet traffic jams of the past. So as you stream, download, and connect today, consider this. How did the rigid 53-byte organization of ATM pave the way for the massive gigabit networks we rely on every single second? It's a true testament to the power of structured engineering. Thanks for joining me on this explainer, and keep learning.